Röntgen's discovery of X-rays excited all of science. Not since the time of Galileo had anything shaken the scientific world so thoroughly. Many scientists had grown smug and self-satisfied, thinking they had all the answers. Röntgen's unexpected discovery left these scientists completely astounded. Very quickly, experiments uncovered other wonderful findings. The year 1895 marked the first year of a decade that became known as the Second Scientific Revolution. Henri Becquerel, a Frenchman, saw X-ray photographs for the first time on January 20th, 1896. Wilhelm Röntgen had sent them to the French Academy of Sciences. Henri Becquerel, a Frenchman, saw X-ray photographs for the first time on January 20th, 1896. Wilhelm Röntgen had sent them to the French Academy of Sciences. Thoughtfully, Becquerel examined the photographs. Until then, Becquerel had studied fluorescent crystals. These crystals glow when struck by ultraviolet light. Special lamps are needed to give off ultraviolet light, or sunlight itself can be used. I don't want to merely repeat Röntgen's work, Becquerel told his friend Pierre Curie. I'll strike out in a new direction. Maybe ultraviolet light will cause your fluorescent crystals to emit X-rays too, Pierre Curie suggested. Henri Becquerel decided to try an unusual experiment. I'll wrap a piece of photographic film in thick paper so sunlight can't get through. Then I'll put a fluorescent crystal on it and leave them in bright sunlight. If the crystal does change ultraviolet light to X-rays, they will go through the paper and fog the film. He set the photographic plate with the crystal upon it in the bright sunlight for a few hours. When he developed the film, it was only slightly fogged. It needs more time in the sunlight, he decided. He wrapped a fresh piece of film and set it outside. Clouds rolled in right away and covered the sky. Henri Becquerel put aside the fresh film in a desk drawer. Days passed. The bad weather showed no signs of going away. He must have lived in Ohio. Growing restless, he developed the film anyway. He expected the film to be clear. After all, the crystal had been exposed to sunlight for only a few minutes. To his amazement, the film was nearly black. It had darkened as though exposed to bright light. What can be the reason for this, he wondered. Henri Becquerel wrapped another piece of film and left it in a desk drawer. After waiting as long as he could bear, he developed the film. Becquerel explained to Pierre Curie what must have happened. I kept several different samples of crystals and ores in my desk. One of them must have given off invisible rays, perhaps even X-rays, he concluded. They penetrated the paper and exposed the film. But which one? Pierre asked. By a series of experiments, Henri Becquerel eliminated one sample after another. Finally, he found the source. It was pitchblende, an ore of uranium. A German chemist named Martin Klaproth discovered uranium more than 100 years earlier. He could find no particular use for the metal. Klaproth feared his discovery would soon be forgotten. The planet Uranus had been discovered a few years earlier, so Klaproth named the metal after the planet Uranus in an effort to keep it before the public eye. Uranium does give off invisible rays. It does so all on its own. Ultraviolet light isn't needed. Uranium atoms undergo radioactive decay. All of a sudden, a uranium atom will break apart. It throws out powerful X-rays and other particles. Although Klaproth discovered uranium in 1792, its radioactive nature had gone unnoticed for 100 years. After Henri Becquerel's discovery in 1896, uranium became famous. It is still the most common radioactive element. During all of this, Henri Becquerel talked at length about his project with Pierre Curie and Pierre's new bride, Marie. The Curies offered helpful suggestions to Henri. In fact, Marie coined the name radioactivity for what he had observed. Henri Becquerel said, "I've proven that radiation from uranium is like X-rays, but even more powerful." Are other elements radioactive? Pierre wondered. Henri Becquerel shrugged. "I've not looked into that idea. My uranium studies take all of my time." He suggested that the Curies start the hunt for other radioactive substances. They readily agreed. Marie began the search for radioactive elements in 1896. Excited, she found pitchblende to be radioactive, even with the uranium removed. Marie said, "It is even more strongly radioactive than uranium itself. Pitchblende must contain more than one radioactive element." In 1898, the Curies isolated a new element from pitchblende. It too turned out to be radioactive. They named it polonium after Poland, Marie's native land. Even the presence of uranium in polonium could not account for all the radioactivity that came from pitchblende. Another element remained. Although they did not actually see the element causing the radiation, they gave it a name, radium. Its name comes from the Latin word radius, meaning ray. Finally, in 1902, the husband and wife team collected enough radium to fill a tiny glass tube. In all, they went through 6 tons of pitchblende to extract about 1/300th of an ounce of pure radium. It turns out that radium is 100 million times more radioactive than an equal amount of pure uranium. For a few years, clockmakers used radium in numbers and hands on clock faces. The clocks could be seen at night. Watchmakers stopped the practice when they discovered the dangers of radiation poisoning. Rays given off by radium can destroy human tissue. Henri Becquerel learned this when he carried a sample of radium with him. He suffered a bad burn because of it. Radioactive material can destroy human tissue. However, when carefully controlled, radium can destroy cancer growths within the body. Some cancer cells are more sensitive to radioactive rays than normal cells. When exposed to rays from radium, cancer cells are destroyed, but healthy cells survive. This process immediately took its place as another powerful tool in the treatment of disease. The process is known as radiotherapy. When doctors realized that radium could fight cancer, it became one of the most sought-after materials in the world. Paris opened a radium hospital. Elements not normally radioactive can be made so by exposing them to radioactivity. The body can't tell the difference between a regular element and the same one after it has been made radioactive. Certain organs of the body absorb some chemical elements more than they absorb others. Bones contain a higher proportion of calcium than the rest of the body. The thyroid gland contains an abundance of iodine. Radioactive iodine fights thyroid cancer. It is mixed with a special salt. The patient eats the salt, and the radioactive iodine is carried to the diseased thyroid gland in the patient's neck. There, the iodine builds up, causing the tumor to wither and die. Just as iodine is picked up by one gland of the body, so other parts of the body collect other chemicals. Radioactive gold settles in the liver. Phosphorus ends up in the bones. Chromium is taken up by red blood cells. By making these elements radioactive and finding harmless ways of giving them to patients, Cancer in various parts of the body can be treated. Chromium is taken up by red blood cells. By making these elements radioactive and finding harmless ways of giving them to patients, cancer in various parts of the body can be treated. In addition to radiotherapy, radioactive elements are used as tracers. The motion of trace elements of radioactive elements can be followed throughout the body. Only very minute amounts of radioactive elements are needed, far less than would cause injury. For example, minerals in plant food are made radioactive. By means of a Geiger counter, a scientist can follow the carbon and see how the plant uses it. What can be done with plants can be done with the human body too. Suppose a medical researcher wants to learn how a new drug works. He can use a radioactive tracer, carbon perhaps, in the manufacture of the drug. Doctors watch the dose of the radioactive drug as it goes through the body. They learn how much is in the blood at various times, how fast it passes out of the body, and where some of it collects in the body. The dual nature of radiation is interesting. Used carelessly, it causes pain and injury. Used cautiously, it has become a powerful tool for fighting disease. God created the forces of nature for the benefit of mankind. We must discover the proper ways to use them.